Let's say this is you, or this, I don't judge. You love playing guitar, and you one day have decided to fulfill your lifelong dream of creating and selling your own line of guitars. As luck has it, you also happen to be a brilliant programmer. So you decide to create your own application where you will sell an option of the guitars you want to build. As your app becomes more and more successful, you start adding more complex features, notifying if someone bid on the same guitar as another customer, if an auction is about to end soon, if an auction has started, and more and more. And you also, of course, want to support all of the different application platforms, such as iOS, Android, and all of the different browsers. All of this mess might be handled by different backend services, each managing some kind of communication with all of the different clients. Android devices notifications should be sent to Firebase, iOS to APNS, web apps via WebSockets, not to talk about considering managing different code bases for different platforms, each having to replicate the same logic. And on top of that, each domain might want to send different notifications in different formats. I'm sure this scenario is not rare at all, and that most companies have faced it in one way or another. And in fact, this is the exact scenario we had to deal with at Vonage. Luckily for us, there is a magical solution. And this is the exact story I would like to share with you today. My name is Ori Shofman Shimoni, as was mentioned. I am a team lead at Vonage and have been here for the past 3.5 years since the corona, a year and a half passed. A little bit about me, I love playing guitar, as you probably guessed from the intro. I love playing chess and football and a big fan of Real Madrid. But most importantly, I'm a big animals lover. And today, this is actually the 1-year anniversary from when we adopted my beautiful dog, Nala, as you can see here. Today, I will share the story of why we needed a messaging bus solution, how we implemented it, and how it has progressed over time. I will show how we decided to implement our specific solution, some good RabbitMQ practices, and several ideas and concepts in the realm of deployment, load, monitoring, and sharding. So let's start from the top. Who are Vonage and what do we do? Vonage builds communication solutions all across the spectrum, from video and instant messaging to voice over IP and fax. And we aim to leverage our platform across various use cases, such as building cloud communication applications for end users. And also we provide all of our capabilities via APIs for developers to use. VBC, Vonage Business Communications, is our main unified communication solution. Its main goal is to provide businesses with ways to communicate within the company and with their clients and customers. Examples can be video meetings, team messaging to chat within the company, and SMSs from outside the company, and a whole lot more features. VBC, as most of the customer-facing products today, depends on creating a good user experience. One of the key components for giving the customers the pleasant experience is making sure VBC is as responsive and as interactive as possible. All of our features heavily depend on responsiveness. You were invited to a meeting, get an invitation on your computer. You received a message, get a push notification with the message content. A few years back, most of these capabilities were done via polling mechanisms. It is fairly easy to realize why this approach has many disadvantages. It is not fully real-time. It created a lot of heavy load on our backend services, and we had to write a lot of client-side logic and to make it handle a lot of the heavy lifting. The list can go on, of course. And so we have made a decision to provide a real-time solution we call the messaging bus. Its purpose is to provide our domains with an easy and flexible way of interacting with the end users and provide them with real-time changes and notifications happening in all of our domains. The main architecture we have decided on contains the following requirements. Number one, client-side connection. We wanted to allow our client-side applications and all the different platforms to register the user to receive notifications. We wanted to allow the clients to register both to receive notifications via live connections like with WebSockets or to be pushed like with mobile push notifications or webhooks. Also, each user will be able to pass a set of rules which will later on determine which message we should actually send to this user. The second side is the server-side integration. We wanted to allow any backend services we had in the company to send any type of notification they want to any set of users. And finally, When implementing such a flexible infrastructure, we need to determine a common language that anyone wants to integrate with us would be able to use and easily understand. This is the language we have come up with. First of all, we need some kind of separation between sets of users. The highest level of separation we have chose is a namespace. It can be used to manage large subsets of users. For example, we can have different namespaces for each application we support at VBC, like VBC, at Vonage, sorry, like VBC, APIs, VCC, and the other terms that you might not understand. Next, we separate the set of users to different application IDs. Same as namespace, application ID can be any kind of ID. But for us, this was really convenient because all of our applications heavily depend on account management, and each account has its own content and ID. Here I have showed some examples like a law firm, a bakery, a gaming company, and a vet company. Each has their own account, and each wants to have only the context of a specific account. After we have our separation, it's time to set up the resources that will live inside of these domains. The first is a subscriber. And as the name suggests, this is a resource representing some client that wants to receive notifications. We added two main attributes to it. The first, a communication type. And with this attribute, it can tell us how it actually wants to receive notifications, like I said earlier, WebSocket, mobile push, webhook, or whatever. And the second attribute is a set of subscriptions. And these are actually the rules with which the subscriber will be able to tell us what messages they want to receive. For example, in the law firm, we can see a consultant lawyer registering for notifications on major cases, both on the web and mobile, as major cases are important. And finally, we have our last resource, the messages. Messages are the resources that backend services use to communicate with the client applications. And like the subscribers, we set two main attributes to it. The first one is a payload, and this is just a completely generic object that the client should be able to process and understand from it what the notification is actually about. And the second is a set of rules as well. According to these rules, combined with the rules the client sent us, we are able to route each message to the correct set of users. Here we have some examples like a new voicemail to Shelly the baker discussing some order, or a new video chat invite to a vet working in Puppy Corp by a concerned dog owner. And now that we have our common language, we can start actually building our infrastructure. In our initial design, we have set up 3 components. So let's go ahead and review each of these. First of all, and most importantly, this is after all a RabbitMQ Summit. We will use RabbitMQ as a messaging broker via the powerful AMQP protocol. I want to go over some of the notable decisions we took in the context of RabbitMQ. So the most obvious one was to use the RabbitMQ cluster that provides easy to manage and provides a lot of advantages. For the exchange type, we used the headers exchange, and this is just so powerful because of its flexibility and the way we can create rules. Third, we used the RabbitMQ management plugin mainly for 2 reasons. One is to use the API it provides to collect metrics, and the second is to handle with it user permissions. And lastly, we used the federation plugin to have one broker serve as a publisher and a set of brokers as subscribers to messages. Now that we have the heart and brain of our messaging bus, we need to have an API which will manage all of the public communications. And for that, we have Frizzle, a Java and Spring-based API serving and exporting all of the APIs we want to manage. Frizzle's API is based on the common language I've showed earlier, and this way we can provide a single yet flexible communication. Frizzle directly communicates with the RabbitMQ cluster, and to do that, we use the Spring AMQP package and base our communication on a channel-based communication. Channels are basically a logical way to handle multiple requests within a single socket. And finally, we have reached our final component. For the communication with the clients, we decided to use the WebSocket protocol. It is a common protocol. It has a lot of support and ready-made packages for each of the platforms we wanted to use, like iOS, Android, all of the web browsers. But because we still wanted to leverage the power of AMQP RabbitMQ provides, we created a simple WebSocket to AMQP proxy, which communicates the client-side applications via WebSockets and then listens to new messages from the RabbitMQ broker via AMQP. Now that we have our infrastructure ready, we are ready to go to production, right? Wrong. When deploying a new infrastructure to production, and even more so when deploying an infrastructure that we know will have to handle a massive amount of traffic, we need to make sure it won't crash and burn at the first sight of pressure. So how do we know that we are ready to handle all of this pressure? A system should be able to handle the necessary load it will face in production. It should be stable and not be bothered from any spikes or unusual behaviors in production. And of course, it should be able to scale over time. And to test all of these subjects, we need some kind of load testing mechanism. And exactly for that, we have an amazing package called Locust.io. Locust.io is a package written in Python. It has a very specific yet powerful set of capabilities. It allows you to create different user behaviors doing the thing you love the most, writing code. You write in Python the user behaviors and then configure Locust to run different volumes of load using these behaviors you have written. Now that we have our load test implementation, let's go through several types of load tests you should actually apply on your system. And the beauty of all of these different types is that most of them can actually be tested using the same implementation you have written for your load test, just with different configurations. The first and most basic one is load testing. With this type of testing, we want to simulate the load that the system will have to handle in production and just make sure that we meet our KPIs. This test is crucial because it gives us the initial okay that we can actually deploy our system to production. Next, we have capacity testing. What we want to do here is basically pile up on the environment until it crashes so we can see what limits we have. This kind of test can help us find some non-functional changes we can apply to improve our performance. For example, finding out if some service saturates some resource like RAM or CPU, and if by changing this resource's behavior, the service might be able to handle more traffic. The third type is called stress testing. We simulate spikes of traffic while being an average load like in production, and then we can see if the system remains up and stable while also handling all of these spikes. This is important because production environments can be unpredictable and you want to make sure no such behavior will cause issues to your system. And finally, we have soak testing, running load tests for long periods of time so we can really simulate what would happen in a production environment. The thing about production environments is that they never rest. They work 24/7, 365 days a year. And if your system can manage, for example, 2 hours of load, but after 2 days, it reaches some limits and crashes, you have a problem, and it is a good thing you found about it now before it happened in production. Now that we know what we want to test and how will we test it, I would like to share some good practices we found really helpful to maximize the insights we had from running these different tests. The first one, make sure you limit the load to the specific set of services you want to test. If you take every single dependency your system has from other teams, third parties, or even irrelevant services in your actual team, it will make understanding what the bottlenecks are and what causes them an almost impossible task. It's useful to simulate the parts you don't actually want to test and to narrow your investigation to what actually matters only to you. Next, make sure you monitor as much of the load environment as possible. Monitor requests, latency, OS metrics, whatever you feel like you want to test. And a lot of very good insights we had were due to the fact that we had an entire view of what was happening under the hood, and not only at the highest levels like APIs. Next, make sure you have a strict set of KPIs before you start testing. What latencies will your product manager accept? How many users will you have to handle in production? And the list can, of course, go on and on. Remember that if you test without knowing what results you're expecting, you won't actually be able to tell if you have succeeded or not when you finish testing. And finally, this is a no-brainer, but I guess still worth mentioning, make sure you have breathing space with your current load in production. You don't want to be the reason of a production incident just because the traffic in the system grew over time, as any successful system does. So what did we find out from all of these load tests? We found out that using the federation plugin and the way we have configured it created a bottleneck, and we decided to go with one cluster of RabbitMQ for the entire system. This plugin is very powerful, but it didn't fit the architecture we have decided to use, and we weren't able to actually figure that out until we simulated load on our system. Next, we decided to switch from headers exchange to direct exchange. Headers exchange, as you all know, is extremely flexible, but it costs a lot in performance. Direct exchange can make your life a little more complicated with managing bindings and rules, but it pays off with its amazing performance. We also changed from channel-based communication to connection-based communication in the Spring AMQP package. And this was mainly because sometimes we saw uneven traffic in the RabbitMQ instances. For example, one of them took several sockets and then all of the channels were connected to it. When we switched to using connection-based communication, we just saw the traffic going evenly through all of the instances we had. And lastly, we just followed some of the RabbitMQ's networking fine-tuning guides for fixing several issues like file descriptors, and also were able to set instances with optimized resources for each service we had. Now we can safely say we are ready for production. But as we all know, life always comes around to punch you in the face. Any live system dealing with a growing and changing environment will just have to adapt, or else it will crash and burn. And on this note, it is story time, where I will share some key changes we did to our infrastructure in order for it to be able to adapt to changes and stay stable no matter what's hit it. So let's get right ahead to our first story. The plugin that loved eating RAM. After a few months in GA, as our load gradually increased, we started to have almost daily production incidents where one or more of our RabbitMQ instances would crash. When investigating, we saw that the RAM usage of the instances would increase until they would actually crash. And after some more research, we were able to narrow down the RAM consumption to be mostly made by the RabbitMQ management plugin. We first tried using instances with RAM optimization, but it only prolonged the time until the instances were crashing. We contacted Pivotal to see if they can assist us with the issue. And after investigating our infrastructure, they explained that the management plugin may not suit our infrastructure and that there are other RabbitMQ products that we are able to use to have the capabilities we need. The two main usages we had with the management plugin were, like I said earlier, user management and cluster metrics. So how will we be able to remove these dependencies without compromising the quality we have? So like I said, there are several ways RabbitMQ can allow us to have these capabilities. And what we have decided to do was, for the user management, we leverage the RabbitMQ backend authentication plugin, which allows us to create our own user management service. We created a very lightweight sidecar to sit with each RabbitMQ instance and provide an API for the user management. And for the metrics, we have leveraged the fact that actually RabbitMQ CTL can provide us with all of the necessary metrics. So we just created a cron job to query the CTL and pass the metrics forward to our monitoring infrastructure. With these two changes, we were able to remove the management plugin from our infrastructure, and we never had any RAM consumption issues ever again. On that happy note, we can move to our second story, the apple that won't push. After a few months of usage via WebSocket Live connections, we added the capability to send push notifications to iOS and Android devices. Clients could create subscribers, like I described earlier, for mobile push notifications, and backend services could decide if a notification is actually important enough to be sent as a mobile push notification. For example, a new message or a new phone call is important enough to be sent as a push notification, but an indication that someone read your message is not that important to be sent. To provide these capabilities, we created a new service in our infrastructure we called PushMe. PushMe manages all the heavy lifting that needs to be done with mobile push tokens and integration with the iOS and Android backend Firebase and APNS. The opposite way, but yeah. Once we already had this capability in production, we were notified about new changes in the iOS push notification mechanisms set to be released with iOS 13. There were a lot of changes in iOS 13, but the two that were most relevant to us were voice over IP push type. So the push type of voice over IP had a specific reason all along for its existence, and it's to be used to present a call screen on your phone. Where in prior versions of iOS, it has been used for other purposes, and Apple just wanted to enforce the usage of it to be only for push notifications for call screens. This meant that any service we had in our infrastructure that used this in the wrong way would actually have to change the way they send push notifications. The second, and this was a very crucial one to us, several types of push notifications were forced to show an indication on the screen of the phone. This meant the notification that the notification we send to some mobile device will have to show something to the user while the notification arrives. And why would that be so critical to us? Because until then, we manage features like do not disturb and mute in our client-side logic. We just got a push notification, and the mobile application code would internally check if the user wants to see an indication or they didn't. And now, if we send a notification, it might be one that the user didn't want to see. For example, a message from a group that the user has muted earlier. We decided to implement a new set of capabilities in PushMe to adapt to the challenges iOS 13 was about to bring. The main reason we decided to do the changes in PushMe was because this way all of the clients and backend services won't have to create specific logic for each use case. They could just send us attributes and headers matching to what we have decided, and we can take care of the rest. So the first thing we added is fairly basic. We allowed the different services to pass an attribute indicating what push notification type they want to send to the APNS. And in our internal logic, we did all the tweaks we needed to do for each type of notification to be sent. The second was a muting mechanism. Because we had to block notification before they were sent to the APNS, we needed some kind of gatekeeper. What we have decided to do was to allow the clients to communicate to the bus which features they want to receive notifications from and which they didn't. This way, even if a backend service sends a notification they shouldn't have sent, PushMe can block this notification and make sure the user won't be interrupted with it. And finally, we have established an event versioning mechanism. Now, why we do need that in the first place? Well, if you work with mobile applications, I think you can easily relate to this one. Mobile, unlike web, has a tail of legacy versions of your application by design. So even if you fix issues and create great products, you will still have a set of users using older versions of your application. And where does event versioning come to play? Imagine that a team wants to start sending a new type of notification, one that might cause issues to older versions of our mobile applications. We want to make sure we safely block this new notification from any mobile app with a version that is incompatible with the new notification. And to do this, we use event versioning. Each client application lets us know what version of events they want to receive from each feature. And if a team decides to send a new feature for a new notification for a new feature, they can just bump the event version and be confident they won't cause issues to the older clients. Finally, all of these capabilities help us make sure that no change in iOS 13 would cause problems to any of our users. Moving on to our third and final story before we go to bed. Well, I'm sure all of you are going to continue with the conference, but for me in Israel, it's already late at night and I need to celebrate Nal's anniversary with us. Our final story is called Taking a Bus Ride with Shredder. As time went by, more and more types of clients and backend services started using the bus. The load continued to increase, and the importance of our stability has become crucial now more than ever. And to handle this, we have created a plan where we would scale horizontally and limit blast radiuses of incidents. We wanted to be able to separate our clients and messages to a number of RabbitMQ clusters, where each cluster will be used as a single shard. With such an architecture, we could add new clusters over time without interfering with the existing clusters. When implementing a sharding mechanism, it is important to decide on a consistent way of allocating resources to shards. You want to be certain that a set of users that have something in common will always be allocated to the same shard, and that each message that arrives to the bus will be directed to the correct shards where the relevant users are allocated. We leveraged the fact that our clients and messages were separated by a namespace and application tuples. So this meant that all the clients sharing the same tuple could be hosted in a single shard, and all the messages with the same tuple would be sent to the same shard. This way, we could randomly set tuples in different shards, and even if a RabbitMQ instance or even if an entire shard has some issue, the issue would only affect the scope of the users hosted in this particular shard. And so Shredder has been created. Shredder is a service that manages the allocation of the users to the existing shards. It uses the AWS APIs to gather information about what clusters and shards exist and allocates clients to these shards. Among its responsibilities, it also manages allocation when we scale up a new shard and drain shards when we scale down. This way, we can theoretically have unlimited number of shards without having any restrictions. We also dabbled with the idea of shuffle sharding, but never actually got to implement it. Shuffle sharding is the concept of setting the same resources in a number of shards. And this way, even if a number of different shards have some issue, only the exact set of users who use only the impaired shards would be affected, as you can see in the example here. And this concludes the stories I wanted to share with you. And now we have reached present days. Today, the messaging bus is a crucial part of our infrastructure and provides our clients with real-time user experience, no matter what application, feature, or platform they use at Vonage. In the near future, we plan on making the bus multi-region, which is a crucial aspect of application high availability. But as you've probably seen by now, we can never know what life will throw at us, and we always want to stay on our feet to make sure we adapt to any change that will come our way. I really enjoyed creating and giving this lecture. Thank you very, very much, and you are welcome to ask me questions.
Ori, thank you very much indeed. A really, really interesting talk there, and hearing about how you use RabbitMQ and the flexibility. We have some questions. We have a question. Yaron, would you like to unmute and ask your question?
Yes, thank you. So I was wondering, like you said, that if you're losing a shard, some of your users will be impacted. So I wonder if you were considering any high availability for this shard, for example, replicating to a standby cluster.
We actually do consider these things now when we are discussing the multi-region. We didn't consider it when we were creating the sharding mechanisms, but yeah, it's a good point.
Okay, thank you. And I'm curious about the user management and the cluster metrics. So in terms of what options you considered to get metrics out of the cluster, you went with RabbitMQ CTL. Were there any other options that you considered?
We actually didn't find any better way, because when we used the management plugin, we just had the API it provided, and then we used, like, as part of the tick stack for monitoring, we used Telegraph, which has a plugin to communicate with the management plugin. But when we removed that, we just didn't find any other good enough tool to, some of them had some of the metrics, but not all of the metrics we wanted. And with the RabbitMQ CTL, we were able to be more flexible. Okay, that's interesting. Yeah, there's a Prometheus plugin that's out available now, but maybe wasn't available at the time. Yeah. If anybody has any other questions, then please add them into the Hoover platform. I'm also curious about the Locust .io that you used. Can you tell us a bit more about that, and how easy would it be for others on the call to implement similar tests to the ones you did? Yeah, sure. So actually, when we started, we had, I don't even remember what's the name, some like Apache-based solution, if you know where, JMeter, okay. We had JMeter in the company, which was like it has a user interface that you would select like boxes and try to create your Lotus that way. And because we had like a complex need for the load testing, we were just not able to use it. I had really a hard time trying to use the thing. And then someone at the company introduced me to Locust. And the amazing thing about it is that it is really, really simple. It has like, I don't know, 4 or 5 APIs that it allows you to use. You just write in Python the user behavior you want, like you want, every 5 seconds you want to send a message, you want to connect via WebSocket, you want whatever you actually want, you can write the code for it. And then when you run it, you can scale it up with, slaves and main clusters. And we were just able really quickly to, test with hundreds and thousands of users, millions of users. Got it. Yeah, that's really interesting. I'm interested to hear how you use that. That's good. And in terms of the tests that you were doing, you mentioned to test only what you think's relevant. I'm sure lots of folks are kind of wondering how you chose what things were relevant, or what sort of questions they could ask to find those things out. Yeah, so when we wanted to test, we consider like we had some initial backend services that wanted to use the bus like for voicemails and meetings and messaging, and trying to test with these infrastructures would just be problematic for us, because if we want to test, for example, I don't know, 10,000 messages per second, the actual services that will depend on us might not be able to handle this amount of load, but we want to make sure we will be able. So instead of actually using them, we want to simulate the most basic approach of simulating the messages that they will send, and make sure that our Lotus will be able to handle this amount, so we can try to put this load and pressure on the system.
Okay, all right, understood. And there is a question here. I think Yaron might have had to deal with a family question, so I'll cover this for him. Where do you run the system? Is it on VMs? Is it containers? How's it deployed?
Yeah, great question. I actually had a slide about it, but decided to remove it because of time. So when we started building this, we had a very large infrastructure for continuous deployment, like automated deployment with Ansible that we have made. It was based on EC2, which was, back then sort of okay. Now I'm actually managing a team that is creating a continuous deployment via Kubernetes. But when we did that, we tried to use some sort of the same concept as like Dockers and the virtualizations with containers. What we did was we created a different way of creating an image for each of the services we had. Like no matter what service we had, we by now have like, 30 services using this infrastructure. They each create an image, and then the way they are deployed is basically the same. They are deployed via an autoscale group in AWS, and then they have a target group, Elastic Load Balancer. They have a DNS. They can have a certificate if they need like they can have an HTTPS certificate. They can be public. And we basically created the infrastructure that no matter what service has to be deployed, they just have to create the AMI image, and then we will be able to deploy them the same.
Right. Well, that's really interesting. Thank you. Thanks for describing that.
Yeah, actually, one other thing, I really like the solution, the subject of load testing. So when we created this infrastructure and we created the load testing, we found out that taking the time to build a continuous deployment infrastructure for building the load infrastructure intact with the bus infrastructure was so useful for us. We could just click on a button, and a few minutes later, we would have an environment in dev that we would just go to the UI of the load test, click start, and we could run load tests like that fairly easily. That way we had months where we did several tests a day with the load, because this is one of the critical aspects in our system.
Right. So you were linking both the deployment mechanism and then the load testing, and just allowing them to, well, not quite to trigger one another, but allow you to easily trigger one once you've deployed it.
Yeah, exactly.